This is Official Nerd Business.
Hello nerd boys and girls, welcome back to our programming series. Today we are taking a crack at Euler problem number 30. We will be using Python 3 to solve it. And let's dive into it. As you can see on screen, I have created the default template I always make with the title, with space for parameters, with description, type and a default value, and with the problem description. And this description states that it is surprising to see that there are only 3 numbers that can be written as the sum of 4th powers of their digits. Then there's the 3 numbers in question, where 1634 is broken up into its digits 1, 6, 3 and 4. Each is raised to the 4th power, yielding 4 and something else. And when added together they all sum back to 1634. Same goes for these 2 other examples. And if you take the sum of those input numbers, then we get back to then we get the resulting number of 19,000 something. And a special case 1 could be considered as 1 to the 4th, but it's not a sum, so it's not included. So this could have been raised by 1 and we wouldn't have this particular exception. But I thought this worked too. Find the sum of all the numbers that can be written as the sum of 5th powers of their digits. Let's think for a second. We need to be able to break up numbers, raise their digits, sum them back and check if this is equal to the input. So let's start off with that. That's a core requirement of this function here. So and as said before, this also needs an input number, so let's use x as any given number and use the nth power, or in fact we could call it power. Now x is an integer in the form of something with several digits. So how do we get each individual digit? We first need to cast this to string. Then we need to say we want to get a list out of this, and the list itself should be integers again. So if we use int so this would now turn this into a string, get each character. Unfortunately you can't pick individual digits out of a number. You need to cast it to string and then treat every individual character as you get them one by one out of the string, and then cast those back to integers. So now x, but I should make this turn this into digits. Digits now is a list of all the digits of the number 1025. Let's make that into x. So now the x that gets put in here gets converted into this digit list. Let's check out how that works. For I in range. Alright, here in the output all the nons are because we are calling functions and then printing something from the function to screen, yet we don't yet have any actual return values. We're just using prints here. So here's 100 in a digit list, 101, 102, etc. So this seems to work as expected. Then this would save me a lot of those nons. Yes. Let's see now. We want to raise each digit to this given power. So let's try that with 100. Yes, these are fourth powers, because we've input 4 in this function here, which goes to run, which goes to attempt number 1, which does nothing, then test our raising function. And now we have a list of numbers, but in actuality we don't want the list, we want to return the sum of its digits. Now note that this could be inlined. I can just simply take this list constructor, the list comprehension, and put it into here. But for clarity's sake, let's leave it as 2 separate statements for the moment. We might consolidate in the future. Now that is on its own, we do print this again. And we get a set of sums. And yeah, 1 is obviously in this list, but that didn't count. And these were the input were numbers from 100 to 200, and we don't seem to have many of those in this list. This one's just short. Here's one, but I don't think that'll be equal to its own input. Alright, so now we need to check if I is equal to its to this. Then this seems to work, and eventually we want to print everything or return. Let's return. Let's do this properly. Return solutions. Alright. So now we have an empty list because we are checking the range 100 to 200, and we didn't find anything for fourth power. So this is basically this example. So we could say that we start looking at one. We have, as long as we don't analyze this problem any further, we wouldn't have any reason to look. Oh, 1 itself didn't count. So let's start at 2 and let's run all the way up to 10,000, because we seem to be finding hits up to about 10,000. So let's plug this in here and let's go. And this finds the three solutions mentioned in the example. So if we were to run main.py, maybe we'll get lucky. And let's run, no, not Euler, run main.py. Here we go. I want to run problem number 30, and I want to use the default parameter. And we get 2 numbers, only 2 numbers. We are forgetting something, however. We want to return the sum of these solutions. So let's run main.py for 30, and it gave us the answer 8,301 in, well, pretty fast, so 1 second. And I can spoil it right now for you. If you go over to Project Euler and you enter this number, you will get the red cross. Yes, this answer is incorrect. We are missing, we are still missing sums of digits, fifth powers, that do count back to itself. to the starting number, and that means that our upper bound is too low. But will this be high enough, or will this be high enough, or maybe even this? Where can we find the maximum of numbers that do this trick with fifth powers? Pause the video and see if you can work out an upper bound on your own. Alright, let me show you how you can determine an upper bound for this particular challenge. Let's say that our number consists of only 9s. Then the sum of this would be 9 to the 5th. 59,049. So apparently, if we look at one digit, then this is the maximum value we can get. So anything at 7 to the 5th or 3 to the 5th could all in theory make themselves again and fit the formula. What happens when we take a look at 99 to the 5th? Well, this would break down when we, or not 99 to the 5th, but the number 99 itself. So this is 9 to the 5th. Is simply this. If we were to look at two-digit numbers and we get a maximum of 99, then we would have twice this, which would be about 120,000. And from this point on, I'm not going to look very specifically at this value, but we could do with the order of magnitude. So if we were to do the same trick for 3 digits, we would simply get this, but 3 times. So we add this one in again, which would land us at about 180,000. And as you might notice, we are gaining. When we first looked at this number, then the difference between even the orders of magnitude between 9 and 60,000 are pretty big. But the order of magnitude has been the same for 2 iterations, and the order of magnitude of the input number has grown significantly. So apparently we are going to cross each other at some point in the near future. So let's have a look at this number. And obviously you can, I'm now typing this out as part of an example, but you could easily script this. In fact, let's. I am going to, instead of printing this, I'm going to do the following. For I in range 1 to 10. So I'm going to make a test number, which is not actually a number. I am going to make it a number, but it is in fact going to be a string of 9s equal to I, and then I will print not only I but also the raise to nth of I to the 5th. So this is going to blow up our digits into the factor sum again, or power sum. And if I now run this particular file, we will get a nice listing of something that doesn't quite work properly. Oh, I don't need to input I need to input test. And I is fine, but I also want to see test. There we go. So I made a slight mistake by inputting not the number we are constructing here, but the loop iterator. And as you can see, as this hit 9, we get the number that we were working with before. Now that's fixed, so let's have a look at this. Yes, here we can see that the number of 9s in our number grows every time. So here's 1 9, 2 9, 3 9s, etc. So here you can see that this is working as we might have figured. And there is a point where 1 2 3 4 5 6 9s make a number that's bigger than the maximum sum of digits that we get. Significantly bigger, 3 times bigger. So what does this tell us? This says that there is a number that has so many digits that if we were to sum up to this number, we would never make it on 5th powers of the individual digits of this number. So this in base 10 has an order of magnitude that's larger than whatever its individual digits could produce under 5th powers. So we now have an upper bound. We know that our input could never be bigger than this. It could be a lot smaller in fact, but we know we can stop looking at this particular point because after this there is no number that could possibly generate itself based on its own digits. And in fact, while we're running through this, we could print whatever I does do this, so we get a feeling by how much we were off with our estimate for the upper bound. But at least we have an upper bound. At least we can limit the problem here. We don't have to guess anything about would 100,000 be enough and see the red cross again. We know that there cannot be any number bigger than this that will show the property of having its digits raised to the 5th power, specifically the 5th power, and yielding its own sum back again. So now we have an upper bound, and let's give this a go through main.py. Problem number 30 for the default of 5. And we did find one number bigger than 100,000. And all in all this sums up to 400,000 and change. And I can tell you right now that that is the correct answer. Enter this over at Project Euler and you will get the green check. And it took us this time, it took us slightly more than a second. And there are a couple of ways in which you might be able to improve this. So for instance, if we were to, now we are calculating the 5th power here every time again, but we could do this slightly differently if we were to make a dictionary to store our intermediate values, and then we need to fill it as such. First, because we are going to use this from 2 different functions, I want it to be declared globally. Hang on. For I in range So now we are storing all of the possible individual values for the digits as powers, and I can do this, print power list. So if we were to run this now, we are going to re-enable that, and this is with 4 powers. So we would get 0 and a 1 here, then a 16 and 81, 260, 256, etc. And if we were to do this fifth powers, then again, fifth powers are now stored in this dictionary, so let's actually use them. And again, I want to clearly indicate that we are using the same instance of this variable. And instead of this calculation, we already have a string that, so this cuts out both a integer conversion and a calculation by now using this, and this should speed things up a bit. So this print and return again be removed again. Step 8 wants me to put an enter here, and let's run main.py again. Problem 30, 5. And this was a lot faster. It now runs in 0.4 seconds with the same answer remaining. So that's about 3 times faster than what we just saw. So yeah, that's a bit of optimizing. That's looking at how we can determine an upper bound, and that's raising all of our digits to the 5th power. I hope you've enjoyed this video. I will leave a link in the description for both the challenge at projecteuler.net and for my GitHub, where you can find all of the sources that we've made here. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.